talk about how focused flexibility maximizes the thrust production of flapping wings. So the title looks a bit different from what you're
Yeah, I shortened it. Okay, thank you. Thanks for the introduction. Thanks to the organizers for a fantastic workshop. So a word of caution, my talk is going to be much more application geared. There'll be some complex analysis, but it'll be light, more simple techniques. And I'll focus more on the applications. So as you could see, I'm going to be talking about how critters move themselves through a fluid, either by flying or swimming. It's essentially the same physics going on, where you flap either a wing or a fin, and they propel themselves through a fluid. This is a modern research topic because people are trying to integrate this into new technology. I have a few pictures here. This is called a micro air vehicle. It's based on insect flight, and you can see the scale there. And this movie I want to show you, I'm really glad that I do have the sound because the sound makes it even better. Let's see if, oh, I'm doing it here now. Nope. Okay. Okay, here we go. Okay, so it looks like a glider until you notice how it's actually propelling itself right there. Doesn't have a propeller, it's flapping wings to move forward, and then once it gets enough lift, gets enough speed, it generates lift. And what's more amazing is that there's no engine on board. This is called a human-powered ornithopter. So it's powered by a person inside that pod cycling. Okay, that's flapping the wings. So you could imagine that you need a very high efficiency. Let me mute that a little bit if I can. I can't. Okay, I'll just stop it. I have no control over this. I'm bad at these clickers. What's the speed? Oh, I don't know. I don't know off the top of my head. It's, enough to fly. But the point is, you need a lot of efficiency there to generate enough speed, to generate enough lift. And that's one advantage of these biomimetic technologies. Efficiency as well as agility and stealth, things like that. So it's a topical research. So before I go into my talk, I want to give a little advertisement. The organizers have been kind enough to give me the opportunity to give another talk at some point, which I'll talk about anomalous water waves based on some experiments. And I've been inspired by some of the talks that I saw yesterday with these innovative ways to approach nonlinear PDEs with complex analysis techniques. And this really kind of struck home with me because of this recent work I have. So we did laboratory experiments with water waves, as you could see, going over an abrupt depth change. So you just introduce a step here so that the depth changes abruptly. And you see dramatically different statistics of the surface waves on one side versus the other. You could even see rogue waves on this side. Okay. So we have some work using KDV, but the truncated KDV system. And this is all I'm going to show you today. I'll tell you more later. But upstream, in one depth, you see drastically different dynamics than downstream. Okay. So we've done some work. I think there's opportunity to do more work on that on the theoretical side. So that's why I mentioned it here. Okay, but back to flight. To study this problem of propulsion, I like to start with kind of a simple paradigm system. And so just for concreteness, let's think about bird flight, where a bird flaps its wing vertically, and that produces thrust in the horizontal direction to propel itself forward. Okay. So keep that in mind for now. And there's some very nice, simple experiments that kind of elucidate the same mechanisms. These were done at NYU in the Applied Math Lab. And the main difference is instead of air, we have water. So we have wings and water. And I'll show you what happens. Okay, so we have swimming. And the striking part about this experiment, the only imposed motion is the vertical heaving motion, that up and down heaving. The rest of the motion is emergent. So this circular swimming motion, that's because the wings are propelling themselves. So it's free swimming in that sense. And then the other motion you see is this angular pitching of the wing, and I have the perfect prop here, albeit a bit long. The angular pitching component, that motion is also emergent, so that is not forced. Okay? So that's allowed because this axle here is connected to a torsional spring right in this mechanism here, which allows it to flex and provides that elastic recoil. Okay? So this is the system I'm going to start out by studying. And so this torsional spring represents flexibility of the bird wing in sort of a simple way. And kind of the main findings that jump out is that that flexibility can dramatically improve the performance of the wing. It can make it swim faster, especially if it's forced near a resonant frequency. And I'll touch on that throughout the talk. I can do this. Okay, so I'm going to start out with a simple theory to model this. Going to consider two cases. First, a wing that is rigid and flat and straight, no torsional spring, so it only heaves through a fluid. It's going to be swimming this way, so in the reference frame of the wing, the flow is going past at speed u infinity. And then later, I'll introduce that torsional spring right here at the roots with some spring constant. Okay, so the theory is going to be based on small amplitude asymptotics due to Wu in 1961. So the basic idea is if that amplitude, the driving amplitude, is small compared to the chord length, okay, then the vertical velocity is small compared to this horizontal velocity, and I could linearize the Euler equations. So that this looks like the Euler equations, but where I ordinarily would have that nasty nonlinear term, I simply replace that by the free stream velocity, the constant velocity there. Okay, and on the right, I have the pressure gradient, which here, like Scott, I'm calling that phi. It's a dimensionless pressure gradient. So the nice thing that you could do, these equations are linear now. The flow is incompressible. So you could take the divergence of this top equation, and that divergence now commutes with this linear operator. So you get 0 on the right-hand side, which means that pressure is harmonic. So harmonic function. So I could introduce a complex conjugate function, and all of a sudden I have an analytic function to work with, and now I could use the tricks of complex analysis. Okay, so that's the theory in a nutshell. I should also mention that the Cutta condition is going to be enforced, which allows vorticity to be shed at the trailing edge, and that's really the main thing that allows you to get thrust in a fluid. Okay, so this is a great theory, and it's already been developed by Wu. It's great if the kinematics are known beforehand. So if I have the kinematics, h is the displacement of the wing from equilibrium. If that's given to me, and here I just wrote it as harmonic in time, and I have a heaving component and a pitching component, linear in x. So if that's given, then I could just use Wu's theory, push it through, use the tricks of complex analysis. You see a Joukowsky transform here, which maps the wing, which is a line segment, to the unit circle, and then perform this multipole expansion with a singularity at the leading edge and the rest centered at 0. And I could get all of these coefficients explicitly in terms of the known kinematics. And then I've solved for the flow field exactly. Okay, so great theory if you know the kinematics, but if you don't know the kinematics, that's a different story, which we never addressed. And that's what I want to address, because I actually want to know what the emergent pitching motion of the wing is. and what its swimming velocity is. So I'm going to leverage this theory, but I want to solve for the pitching, which means I have to solve a little torque balance problem here. On the left, I have angular acceleration terms, and on the right, I have all the torques acting on the wing. So this is the torque due to the spring. Okay, so you see that spring constant there, and the angular deflection. And then this represents all the fluid forces. So this box P, that's the pressure jump between the top and the bottom of the wing. And I integrate that against distance, and that gives me the total torque induced by the fluid on the wing.
So your wing is not flexible,
It's not flexible. All the flexibility is located at the torsional spring. Yeah. Okay, so I could use this formula right here to solve for the emergent pitching motion of the wing. And that's what I'll do here. So just rearrange some things. I got to tell you about a few dimensionless parameters that'll come up. Big R, that's the ratio of the solid to the fluid inertia. Okay, the fluid, you could think of this as added mass or added inertia. Big K is a dimensionless spring constant. So it's got the regular spring constant scaled on fluid forces. And then sigma is the reduced frequency. That one's important because I'll vary that a lot. So it's the driving frequency scaled on a time scale of the fluid flow there. Yes?
The torque balance, what is H power?
Oh, yeah, I wanted to gloss that over because it's kind of technical and not that important. That's okay. This is just an angular acceleration term that comes from taking the reference frame of the wing that's moving up and down. That's all that is. Okay, so using Wu's theory, combining it with this torque balance allows me to solve explicitly for these coefficients. Okay, so I impose the overall driving amplitude of the wing, and then I solve for its emergent pitching motion. So this is just really quickly the exact solutions. They're not pretty, but they're explicit, and this is the final result, those beta coefficients, which tell me the kinematics of my wing. So explicit solutions for the motion of the wing. Okay, I'm just going to show you these movies to illustrate what the exact solutions look like. So this is slow flapping, I call it. And these dots just illustrate the speed of the fluid flow going past. Okay, so there is a torsional spring at the root, okay, but the flapping is slow enough that you see very mild deflection. Okay. Now, I'm going to keep everything else the same, except simply increase the driving frequency, and I get a very different motion, right? The pitching is much more pronounced. And this kind of resembles, to the eye, kind of resembles maybe natural motion that you see in the natural world. Maybe a bird wing or an insect wing looks somewhat like that. Now, if I increase the driving frequency even more, you see this, which is again different. To me, it kind of looks like a bird that's trying to flap so fast that it's kind of frustrated, and the pitching that emerges kind of counteracts the forward propulsion. You could see that by the phase difference in the heaving and the pitching. Okay. All right, so what's the performance of these wings? How much thrust do they produce? So I'm going to show you plots of the thrust. This is actually going to be the dimensionless thrust coefficient. So the raw thrust scales like the frequency squared. That's a well-known result. So the thrust coefficient removes that scaling, so that asymptotically you should get flat. And then I'll vary the dimensionless parameters. The baseline is the wing with a stiff leading edge. So the spring constant is infinity. Or that's a clamped wing, a wing that cannot pitch at all. Has to stay straight horizontally. So the black line, that's the thrust coefficient produced by that wing as I increase the driving frequency. And because I non-dimensionalized, you get an asymptote as frequency goes to infinity. So the red curve is this wing with the torsional spring, and you could see very different behavior. You see this peak. So at some intermediate frequency, it produces much higher thrust than the clamped wing. Okay, and so that's connected to resonance. Okay, so experiment with a few different torsional spring constants. So I'm increasing the red curves, I'm increasing the spring constant, and that shifts the resonant frequency up, and it also increases the peak thrust that's produced by each wing. Okay, so now I want to go back and compare with these experiments to see if the theory, captures realistic behavior at all. So these are measurements taken from these very experiments, and I've got to explain what the axes are. So this is the driving frequency, that's this heaving frequency, and then this is the emergent circular frequency. So think of this as swimming speed, okay? So how fast that wing swims in a circle. Okay, so there's two cases. The circle is the clamped wing, okay, and the triangles have a torsional spring, like in this movie. So you see for the clamped wing, the swimming speed simply increases nearly linearly with driving frequency. And then for the wing that's allowed to pitch like this, you see a transient increase, where you get a boost in swimming speed, and then it diminishes below the clamped speed. Okay, so I want to put this into the theory, see if it captures similar behavior at all. But there's an immediate problem here in that the thrust predicted by the theory is always positive for all frequencies, all swimming speeds, right? So what would happen if I set this thing free, like in the experiments, is it would just continue to accelerate indefinitely, and it would never reach a steady swimming speed. Why is that? Well, that's because this is an inviscid theory, right? So when you go to compare against lab experiments, sometimes you have to put back in realistic effects like drag. Okay, so this is a real wing. It has finite thickness and finite viscosity, which means there's drag on it. And so I could just insert that back into the theory in a very, very simple way, very coarse grain, just add a drag term that's proportional to the swimming speed squared. So this is a high Reynolds number drag. Everything is going to be known here if I know the swimming speed, except there's this drag coefficient, which maybe I don't know for a wing. Maybe I could look up values, or maybe I could do something different. What I'm going to do is use the experiments to calibrate that drag coefficient. Okay? So once I do that, well, the swimming speed is going to emerge as the speed at which thrust balances drag. That's the steady swimming speed. Okay, so back to the calibration. I used the clamped wing experimental data and simply fit what this drag coefficient has to be, and that's the black line here. So find the line of best fit, and then I know the drag coefficient for my wing, and now all I have to do is insert this torsional spring, and here I don't do any more fitting. I use the torsional spring constant that was given in the experiments and put it in this theory, find the free swimming speed where thrust balances drag, and that's the red curve that I get right here. Okay, and you can see that this is pretty encouraging. It captures the overall qualitative trend. You see the boost in performance at intermediate frequencies. It even captures the resonant frequency, where the boost is most significant. It captures that frequency very well. At higher frequencies, there's some discrepancy, so it's not a perfect theory. But to me, that's okay, because as coarse-grained as the theory is, there's no finite amplitude effects, and drag is only counted in this very coarse way. I could live with this discrepancy. Okay, so it does a pretty good job of capturing qualitative experimental data, even quantitative in certain regimes. Okay, so that's a summary of what I've told you about so far. For the simple case where I have a torsional spring, all the flexibility is located in one position, I could actually find exact solutions for the kinematics. And this captures the different dynamical states, the resonant frequency, and then the high frequency where you get reduced performance, and even some experimental trends. Okay, so now I want to push this theory a little bit farther. I want to consider spatially variable flexibility. So wings that you see in the real world, they usually don't have constant elastic modulus, and it's not concentrated at a torsional spring either. Usually it's some structured form of flexibility. So this is an example that shows an insect wing, and it has this network of veins here, and they provide structural support, they provide rigidity, but not in a uniform way, in a way that's variable along the wing. And you might ask why this particular network. Perhaps that boosts the performance of the wing in some way. So that's the kind of question that I'm going to ask next. Okay, so I use this simple framework again, the Wu theory, same linearized Euler equations. This is the analytic function again, where phi is the pressure, and that's the harmonic conjugate. The kinematics are going to be different. So now to describe bending of the wing, I won't bend the stick, but describe that bending, I need a full Chebyshev series. Okay, well, a polynomial series of some sort. I choose a Chebyshev series, and the reason is that pops out straight out of the Joukowsky transform that I used. Okay. So in the wing space, a Chebyshev series is going to be a Fourier series on the circle. Okay, and that's the big advantage to using Chebyshev here. Okay, same kind of framework for the fluid flow solutions. If you know all of these coefficients that describe the kinematics, then you could get these coefficients, and that tells you F everywhere, which tells you the pressure everywhere, and then post-processing, you can calculate the fluid flow everywhere if you wanted to do that. Okay, so that part is known, but again, I'm not prescribing the kinematics. I want to allow the kinematics to emerge from the fluid structure interaction. So analogous to what I did with the torque balance, now I'm going to use the beam equation to describe the bending kinematics of this wing. All right, so H again is displacement from equilibrium. This is the beam equation. It's second order in time, fourth order in space. Importantly, here's the elastic modulus, and that I'm going to allow to be a function of x so that it has spatially varying flexibility. Okay. Again, pressure jump between the top and bottom of the surface is the forcing term on the right-hand side. Okay, so I have to solve this numerically now. I can't get exact solutions. And I'm going to use a Chebyshev method based on my Chebyshev expansion here, and it's going to be iterative. So in a nutshell, the way this works, it's iterative, so I'm going to start with a guess for the kinematics, a guess for all these coefficients. Looking at this PDE here, for all the spatial derivatives, I could use fast Chebyshev differentiation, which is a very fast, efficient order n method, where n is the number of collocation points on the wing. Time derivatives are easy because I've assumed harmonic in time, so that's trivial. And then I need the forcing term, which I get from this Wu theory. I get from these exact solutions for F. Okay? So I start with a guess for the kinematics, differentiate the left-hand side, use the fluid flow solutions for the right-hand side. That gives me a residual, which tells me how to improve my guess. And then I use a simple iterative method. I use GMRes until I eventually reach convergence and solve for the kinematics. Okay, so the advantage of doing things this way is that at the end of the day, I have a lightning-fast numerical method for solving for these kinematics. Because the Chebyshev differentiation is order n. This evaluation of the pressure jump is order n. I should say order n log n, order n. And if I precondition judiciously, then I'd take the number of iterations required as independent of n. So overall, I could solve for these emergent wing kinematics with only order n log n complexity, where again, n is the number of collocation points on the wing. Okay, so just movies of what the actual kinematics look like. This is the slow motion, where you see very slight bending. This is near resonance, where you see dramatic bending. And, well, you see a particular phase difference, where it looks like everything is helping. The bending is helping the propulsion. And then if I increase the driving frequency too much, you see these out-of-phase kinematics. Okay, so this is tests of the algorithm. Just to verify the order n log n complexity, as I increase the number of collocation points, this is the CPU time, and you see that it does grow like linearly, order n log n in time. And then the accuracy, this is a convergence test, where I measure the L2 error against an exact solution, or an asymptotic solution actually, as the system size increases. And what I see is third order convergence here. That may come as a bit of a surprise because I'm using a Chebyshev spectral method. You might expect spectral convergence or exponential accuracy. But the reason why the accuracy is not exponential is the form of this fluid forcing term, the pressure jump. In particular, this thing right here. This is a singularity at the leading edge. I should point to this term. The leading edge of the wing at x equal -1. The fluid force is singular there. So that actually limits the convergence of my spectral method. And if you do the calculation, you could actually see exactly why it is third order convergent. So that's been verified by this test. Okay, third order is still plenty accurate enough for me. Okay, and so now I want to start addressing this question of optimizing the flexibility distribution for performance. Okay, I'm going to start out kind of simply. I like to start out with a simple example and build up in complexity. So what I'm showing you here is a simple comparison. This is comparing a wing of uniform flexibility, so the elastic modulus is constant, versus that torsional spring case that I showed you earlier. Okay, so I'm just going to fix the mass ratio, keep that at 1. I'm going to vary the driving frequency. And then these are the two dimensionless parameters that we're going to compare. This is the dimensionless stiffness. This is that dimensionless spring constant from earlier. Okay, so black again is the baseline. That's a clamped wing, okay, thrust versus driving frequency. And this is the uniformly flexible wing. This is the torsional spring. And I chose these two numbers simply so that the resonant frequency would align, so that they would resonate at the same frequency. And what you see, the curves are qualitatively similar, but you see one is above the other, and that's the torsional spring. So you get overall more thrust with a torsional spring than you do with a wing that's uniformly flexible. Okay, and that'll be a theme. That'll reemerge as I go on. Okay, so what happens if I were to increase the stiffness of these wings? So same thing, uniform and torsional spring, just double the stiffness of each. And these are the curves, and again, they resonate at the same frequency, but the torsional spring produces more thrust. Okay, so now I want to address this question of optimization. I want to find the flexibility distribution that's best for performance of this wing. So what I'll do is I'm going to optimize this distribution of elasticity. Okay, I want to optimize that quantity for thrust. And I'm going to start out simple and build up. I don't want to just jump right into the infinite dimensional space, the function space of that, because that would be a very, very tough optimization problem. Instead, I want to build up in dimension. So first thing, I'm going to consider stiffness distributions that are uniform and optimize that single number, optimize that uniform stiffness for thrust. And then I'm going to consider linear distributions of stiffness and optimize that distribution, and then build up to quadratic, cubic, etc. Okay. All along, I'm going to use the result from here as the initial guess for the optimization at the next stage. So that's the benefit there. Okay. So that's, this is kind of what I showed you earlier. These are the two uniformly flexible wings, two specific cases. And now I'm going to go along at every individual driving frequency and optimize this number S for thrust production. That's the curve, that's the curve I get right there. And it just kind of sweeps along the very top of these two individual cases, as it should. Okay? And you see that for a higher driving frequency, if you choose the stiffness judiciously, you could get higher thrust. Okay. So now I'm going to build up in complexity, go to linear distributions of flexibility. Okay, so that's linear and cubic. You get a substantial increase from going from uniform to a linear distribution of flexibility. And then just a little bit of increase from going from linear to cubic, and quadratic is going to be in between there somehow, somewhere. Okay, so what we see is that we already sort of have convergence in this function space of elasticity distributions, okay? Which is to say that if you optimize over linear distributions, that's already pretty close to good enough. So what are the corresponding stiffness distributions? These are what they are. So this is stiffness along the wing, where this is the leading edge, and this is the trailing edge. And I'm showing you the optimal linear and optimal cubic distributions. And you can see some similarities. Both of them have low stiffness at the leading edge and higher stiffness further back, which means that focusing the flexibility near the front, near the root of the wing where it's being forced, seems to give an advantage in thrust. Okay, so what's, if you see that trend, you might ask, what's the kind of most extreme version of that? And that goes back to the torsional spring case that I showed earlier. So what I do now is test the torsional spring case. Again, at every driving frequency, find the torsional spring constant that maximizes thrust production. And that's the dotted curve that I see here. And it just barely beats the linear and the cubic distributions. Okay. So overall, torsional spring, if you optimize the spring constant, seems to perform the best. And this picture just kind of further elaborates on that. So here I'm showing you the thrust from the optimal torsional spring versus the optimal uniform distribution, the ratio of those two thrusts. And that ratio is always larger than 1, which means the torsional spring is always winning. And as it depends on this mass ratio here, okay, you see differences in the curves. But one thing that jumps out at this is in the limit of high driving frequency, they all asymptote to about the same value. And that turns out to be about 36% higher. So you get a 36% boost in choosing the optimal torsional spring compared to the optimal uniform distribution. And that's, we still don't have an analytical grasp on why that's true. It's simply a numerical observation. Okay, so I believe that this principle of focusing flexibility at the driving point actually shows up in nature, and that's in insect hovering. Okay, so what I've talked about already pertains to forward flight, right? Flapping vertically and moving in the forward direction. But to think about insects, you simply have to rotate that picture where you're flapping horizontally, and you're not moving vertically, but you're producing vertical force to counteract your body weight so that you stay in the air. So a simple rotation by 90 degrees, and that's how you could think of insect flight. So there's been some experiments done, both observations of real insects and controlled experiments. And natural insect wings have two types of flexibility, so two sources of flexibility. One is the surface of the wing itself, which you could see, if you look closely, the surface of the wing actually bends a little bit. And the other one is at the joint here where the wing connects to the body, what's analogous to our shoulder joint, right? So that shoulder joint is actually deflecting angularly, a lot like the pitching motion that we saw, okay? And that, again, is not controlled directly by the insect. It's due to the fluid structure interaction. So it's a passive deflection. So a group, I believe this group, I forget, I want to say Harvard, but I'm not sure. A group did some controlled experiments to mimic insect wings, where they did at-scale experiments, which means that they didn't change the scale, they didn't use a different fluid like corn syrup or something. They built wings literally of the same size of insects to test out the lift forces that they produce. And that way, they could control these two types of flexibility independently. So these are two example wings. One of them, both of them have the torsional joint, the shoulder joint, so it's allowed to bend in that direction. And one of these wings is stiff, where the wing surface can't flex at all, whereas the other one can flex, like an insect wing. And so you could compare the forces produced by each of these wings. And what they found is that the wing that's actually stiff and only has the flexibility at the torsional joint produces more I want to say thrust, but lift in this case. So it boosts the fluid force by about 17%. So that's the same principle that the simple theory had borne out, is that if you focus the flexibility at a single point, at the driving point, you could boost the fluid forces significantly. Which tells you that the rest of the flexibility of the wing itself, might be there for other reasons, which we don't know what they are. So they might be there for maneuverability, control, things like that, or it might simply be that you can't avoid some flexibility of the wing using building a wing out of biological materials. Okay, so I realize that I sped through kind of. But this is what I want to do in the near future. All this kind of theoretical framework has been built in the two-dimensional setting, which is appropriate for modeling certain situations and comparing to certain experiments. But if you want to do an application like the human-powered ornithopter, you really have to go into 3 dimensions, because here the bending motion is not in the two-dimensional plane. The bending motion is along the span of the wing. Okay. So I have ideas for how to extend this simple theory. And the idea would be to use something like lifting line theory, but I'll have to adapt it. I'll tell you why in a second. But lifting line theory, to give the salient idea, connects the circulation to a downwash velocity. So you think of each of these sections of the wing as sort of a separate two-dimensional section, and then they're all linked through an integral equation like this, which allows you to extend it to 3 dimensions. Okay, so the classical lifting line theory, if you look it up in a textbook, it's quasi-steady, which means that you could only capture this slow mode of flapping, which we saw only gives you slight deflections. You cannot get to the resonant frequency using classical lifting line theory, and you certainly can't get to that high frequency case where the flapping is out of phase. So what I would like to do is use the small asymptotic theory, but adapt it to 3 dimensions like this. And the reason is you'll be able to capture those different dynamical states. So you're not limited to quasi-steady. And then once you do that, you could study all sorts of interesting problems. Like you could vary the span and the chord-wise flexibility independently, and you could even optimize over each of those to get some complex optimal distribution. And then you could even consider anisotropic elastic modulus. And then, of course, you could vary the planform geometry of the wing. So I think that framework, once developed, it's still kind of a pipe dream, but I think that would allow you to optimize the complete architecture of such a wing so that you could really inform the engineers and tell them how to build the optimal design to get better performance. Okay, I believe that's it, and I'll take questions. I guess I gave us an extra tea break by speeding through, but I'll be happy to take questions.
Early on you mentioned the importance of the vorticity shift in the trailing edge.
That's right.
Then it rather disappeared until really your last slide when you got onto lifting line theory. So I wonder if you looked in more detail at the vorticity, for example, rolling up. I mean, there are complete theories, aren't there?
Yeah, yeah.
Theory, for example.
Yeah.
Deal, I think very much in your spirit.
Thank you. Yeah, I have a few things to say about vorticity. I did sweep it under the rug a bit, which I didn't have to do because I have so much extra time. So as I mentioned, vorticity is accounted for in this theory by the Cutta condition, and it was hidden. You probably missed how the Cutta condition was enforced, but it was the form of this solution. The form of this solution here in the mapped domain. There is a singularity at the leading edge, which is a real singularity, but there's no analogous singularity at the trailing edge at +1. And so that is the Cutta condition. You enforce finite velocity at the trailing edge. So that's how it's enforced in the theory. The other thing that I do want to say about that is a lot of methods, maybe most methods, focus on the vorticity as kind of the primary unknown, the primary variable to solve for. And then once you calculate vorticity, you calculate the flow field from that, and then calculate the pressure, and then you could calculate the bending. So it's this very indirect chain. This method, in a sense, I think has more simplicity conceptually, in that you're going directly, the variable of interest is the pressure directly. So you're solving for that directly without going through these intermediate variables. And that pressure directly tells you the fluid forces on the wings, which bends it. So it is more direct in that sense, even if it's non-traditional, because people are thinking about vorticity. Now, sorry, I'm giving a long answer. But you also mentioned vortex sheet roll-up, which can be an important effect. That's not going to be captured here because I'm in the small amplitude regime. Okay, so even though I drew it wavy for illustration, in the theory, the vortex sheet is always flat. It's always perfectly flat. So it's not going to capture vortex sheet rollup. But having said that, this is something I would like to examine, and I'd like other people to think about it too. This theory compares pretty well to experiments, as I showed you, and other simulations. I've benchmarked it against vortex methods that do take into account vortex sheet rollup. And as far as how the wing moves, the performance of the wing, it captures all of that pretty accurately. So that might be suggesting that vortex sheet rollup, since it happens downstream, is not directly affecting the wing's motion as much. And again, I can't quantify that, but it's something I want to look into more.
When you're doing the experiments at NYU, the U infinity is determined as part of the solution. It's not given a priority. So it seems to suggest that some of your parameters, a parameter needs to be determined versus defined.
Yeah. When I compared to those experiments, I did leave that as a free parameter. So again, the way I determine the free swimming speed of this guy is to find the speed. You see it appears there in the dimensionless in the reduced frequency. So find the value that gives me a thrust balance, where thrust balance is drag. So on the picture, it would be right here.
And so that set some of the parameters.
That sets in the theory, it sets the sigma directly from which you could back out the free swimming speed. Yeah.
So the model is by construction time periodic, which gives responses which might be quasi-periodic or chaotic. Is this a restrictive assumption?
It's a good question. Yeah, that's a really good question. So here, yeah, so off the cuff, I think you would need nonlinear effects to get that response. Here, I've only considered not only time harmonic, but a single mode in time. So again, one thing in the near future is to include other modes. And I think because the equations are mostly linear, I think you'll only get those exact harmonics. I don't think you'll get quasi-periodic behavior, but I could be wrong. It's linear. The flow field is linear. It's linear in amplitude, right? It's kind of funny. There could be. That's true. From the shape of the wing, there could be geometric nonlinear. Yeah. Not necessarily, and it may be a slight boost, but when I did the optimization, where I compared things, right? By allowing a sufficiently broad function space for your stiffness, that implicitly allows everything, and so. Well, if all of my flexibility is focused at the front, kind of like, this is kind of like these optimal distributions are, right? If all the flexibility is focused at the front, then that would allow very close to a rotation, right? So if I had, if my function space were broad enough to include a function like this, right, then that would approximate a torsional spring. And so, what I showed here is that already by the time you go to cubic, you've already kind of saturated in thrust optimization. So there's kind of, even though these distributions look slightly different, or they look, noticeably different, the thrust difference is only very slight. And then the torsional spring beats them all by a very slight number. Yeah. I mean, archetypes have already been built. They're not in mass production, but as you see, even at the scale of humans, they've been built already. Right, definitely not.
So I think you're right that the problem is linear in the context of Gaussian Podolsky. I mean, the closest nonlinear version is the Albert 2010-2014 period, which is very similar, except there's no something made about the Wu equation. I have a question to your 3D stuff. I mean, how similar would that look to the kind of classic Landau and Ashley textbook, right? With this sort of resolve. When the body essentially is an asymptotic version of this very small amplitude wings, so it might look a lot like that with a span. So it might be quite a bit of
Okay.
old design that could be adapted.
Yeah, I'd like to find out more, because I don't know that reference off the top of my head. So. Which effect? Sorry. Yeah. Oh, it's seeing its own wake. It sees its own wake. Ah, great question. And you know this recent work out of the same lab. So these are experiments from longer ago, maybe a decade ago or so, in which they deliberately used range of parameters where the wing was slow enough where the seeing its own wake would not be a dramatic effect. So they deliberately did that to kind of isolate that mechanism. But since then, there's a kind of a new line of research in the same lab where they forced the wing more rapidly so it could swim around faster. And by the time it got around, the wake is not completely dead, and it could interact with its own wake. So that, and there's lots of interesting dynamics that emerge in that case. Yeah. But here it's not happening as much. Yeah. Yeah, to get a complete theory, you would. Yeah, yeah. So, okay. There's not a leading edge vortex in the theory. I haven't. That's not really high on my priority list. But it could be something worth considering. That is more of a finite amplitude effect, the leading edge vortex. So yeah, you would have to extend this theory to the nonlinear amplitude, and either bake that into the model, or hopefully more pleasantly it would emerge naturally from nonlinearity and amplitude. So that's something I haven't thought a lot about, and probably that's more important in these kind of cases where the motion is not fast, but it's closer to stationary, like, for example, the hovering case I showed. That probably could be important in that case. Yeah.
Are there any more questions?
Yeah. What is the ratio between the maximum amplitude of your beam reflection to the span of the beam?
And in the theory or in the experiments? In the experiments or in what? Oh, I mean, in the theory, it's taken to be a small parameter. So essentially, it's my epsilon that vanishes, and everything is linear in that epsilon. So really, it doesn't matter. Oh, the deflection.
Yeah. So the maximum deflection with respect to the span of the beam is what you said.
Okay. I can't quote you the number off the top of my head. I could show you my paper afterwards. I know a calculator at some point, but it's substantial. It's substantial. It's, off the top of my head, I would guess 20, 30, 40%, something like that.
And you still use linear beam theory?
Yeah. Oh, I thought you were asking about the torsional spring case. The bending case. It's still substantial. I would guess less than 20% in that case. And I do use linear beam theory, yeah. Certainly you could add nonlinearities into the structural equations. Probably at that point, if it gets to that point, the bigger need is to add the nonlinearities into the fluid equations too. So I would say both of those things would need to be done simultaneously if you're gonna do one of them. Don't think so? Okay, I'd like to. You think nonlinear elasticity is more important? Okay.
Any more questions? If not, let's thank this.
Thank you.